All right, hello. Thank you so much for being here. You're watching my presentation pre-recorded today because I am currently out on a boat deploying a glider. Um, so I was working with Dr. Donglai Gong this summer on quantifying errors within data-assimilative global ocean models using glider data from the Mid-Atlantic Bight Slope Sea. So for some background, this project was undertaken with data gathered in collaboration with NOAA's Hurricane Glider project. This initiative is informed by the fact that over the past 20 years, hurricane trajectory forecasting has significantly outpaced hurricane intensity forecasting. And this general lack of skill in hurricane forecasting costs both money and lives. Hurricanes have cost the US over $1 trillion in damages since 1980 and have caused over 10,000 deaths. Recently, hurricane intensity forecasts have been shown to improve when they integrate accurate real-time data about the upper layers of the ocean over which they're traveling. One place that this data can come from is from ocean models. But these models in particular are not perfect. In the Atlantic Ocean, the Gulf Stream is one major source of uncertainty. It's a narrow, strong, warm, and salty northwards current that stretches up the east coast and eventually starts to meander off towards Europe, transporting warm water and heat polewards. But because cold water can suppress hurricane intensity and warm water can increase hurricane intensity, accurately representing the Gulf Stream is important to hurricane forecasting. Unfortunately, ocean models have historically struggled to fully resolve the extent and dynamics of the Gulf Stream and the eddies that spin off of it, including the temperature gradients that make it up. One of the ways in which the accuracy of ocean models can be improved is by processing and assimilating real-time observational data from vehicles like gliders and sailplanes, and algorithmically modifying their predictions accordingly. Gliders, which my lab works with, are particularly useful for this kind of data assimilation. They can be safely deployed for months at a time with minimal supervision, but they can be steered, unlike floats, and they can safely gather data during extreme weather events. They can also gather three-dimensional data because they can dip down deep into the ocean. The downsides are that occasionally sharks do like to nibble on them. On the right, you can see a graphic of how a glider typically moves through the water. Gliders have a characteristic sawtooth pattern as they move through the water. At the surface, they transmit position coordinates and some data back to land, and are then instructed to deflate their buoyancy engine, which causes them to sink downwards and travel forwards in accordance with their heading and the currents that they're traveling in. When it hits the bottom of its cast or its downward descent, it inflates the buoyancy engine, causing its density to decrease, which leads it to ascend through the water column back to the surface, where it again transmits data. The picture to the right is of a glider in the lab, not one of the gliders that recorded the data sets I'm using, but a very similar one, just so you can get a sense of what they look like. Our objective for this summer was to investigate how the output of one globally constrained ocean model that assimilates glider data, RTOFs East, compares to the observational data that was collected by two gliders, the Navy Glider 657 and the Navy Glider 738, which were deployed from about October to February of last year. We were broadly interested to find out how accurate the model output was to the data the gliders collected, and thus how well the model was assimilating the glider data it had been provided. We anticipated that there might be some differences because the slope sea and the shelf break are dynamically complicated areas, and the Gulf Stream also poses challenges for modeling. To begin with, all of this analysis was conducted with Julia, which is an open source, high performance programming language. Here you can see two maps. The one on your left is the path that NG657 charted over the course of its deployment, while the right one shows the path that NG738 charted. Note that NG738 covered a much larger geographic area than did NG657, as you can see in the top image. In the larger box, bounded in green, represents the range of NG738, while the smaller blue bounded box represents the range of NG657. This data was a little difficult to analyze because the temperature and salinity field of the Gulf Stream changes with time, and the glider that is recording this changing field is also moving in position, as well as in 3 dimensions. any point on any of these trajectories could realistically represent a time when the glider was actually 1,000 meters below the surface. So I'm going to present some depth transects and some animations to kind of look at this data from a bunch of different angles. But all of them are necessary to get kind of an accurate, bigger picture understanding of how accurate this glider data is to the model outputs. The other complication to this, to my data analysis, was that the glider provides much more finely gridded data than the RTOFS model does. RTOFS is a 1/12th degree resolution model, which at these latitudes kind of works out to about a 4-mile by 4-mile grid and provides forecasts every 6 hours. And a glider moves with the currents, so they can take multiple measurements within the spatial and temporal boundaries of a single model output grid, sometimes up to over 10. So to achieve a glider output grid that had the same resolution as the model output grid, I had to bin all of the glider data by the temporal and spatial boundaries of the model box they were taken in, and then average those bin data and use them to create these transects. All right, so potential temperature. So when we look at these graphs, potential temperature is on top and practical salinity is on the bottom. For each graph, depth is on the y-axis and time is on the x-axis. The potential temperature color bar has higher temperatures represented in orange and lower temperatures in purple, whereas the practical salinity color bar has high salinity values in yellow and low salinity values in green. I'll talk about these more a little bit later, but I just wanted to point out the big light-colored band in the middle of these visualizations. That is the Gulf Stream signal. I also want to point out that even visually, these transects seem to be reasonably similar. Moving on to NG738. Again, we have time on the x-axis and depth on the y-axis. But we can see that the Gulf Stream pattern here is a little more complicated, and it doesn't match up quite as well between the model and the glider, especially past the timestamp corresponding with January 1st, 2022, which is about 3/4 of the way through the transect to the right. We can understand these transects better by calculating some overall statistics of model skill. I chose to use the root mean square error between these models and the bin glider observations. In an absolute sense, the errors associated with the model glider comparison are not negligible, but are fairly low. But although the absolute errors are pretty low, the errors associated with the practical salinity along NG738's trajectory are 32.2% higher than those for NG657. And the errors associated with potential temperature along NG738's trajectory are 48.6% higher than NG657's. To understand why, it helps to consider these series of transects, which represents just the raw difference in value between the model and the averaged binned glider data along each glider's trajectory. So you can see that for NG657, with some small exceptions, the difference graph reflects the visual similarity of the original transects. It certainly isn't perfect, but it's relatively consistent with the low level of quantitative error. But in NG738, this is on the right, this is not quite the case. There's an area of pretty significant divergence between roughly January 1st and January 18th. You can see with the color bar, areas in red represent areas where the model overestimated what the glider said, and areas in blue are where the model underestimated it. And between January 1st and January 18th, the glider moves through an area where the model seriously underestimates the actual temperature and salinity of the water, and immediately moves into a region where the model seriously overestimates the temperature and salinity of the water. And based on the sheer magnitude of these temperature and salinity differences, this has led us to believe that during this time period and in this specific geographic region, the model was not correctly resolving the extent and the kind of landward boundary of the Gulf Stream. So to kind of zoom in a little further on this issue, to the left, we have an animation that I'll be playing in a second of the potential temperature at the 200-meter depth with the glider's trajectory and position overlaid on it. On the x-axis, we have longitude, on the y-axis is latitude, and the yellow end of the color bar represents higher temperatures, while the black purple end represents cooler temperatures. Since one way to define the Gulf Stream is as the area in the ocean where the 200-meter depth exceeds 15 degrees Celsius, I've set up the color bar so that the distinction between temperatures characteristic of the Gulf Stream and those that aren't are pretty visually distinct. On the right, on the right top, we have a zoomed in segment of the NG738 difference graph from the previous slide for easy reference. As we play the animation, you can see that during the period of January 7th to 10th, the glider is in an area where the model records it as being decidedly outside of the Gulf Stream. But when you look at January 7th to 10th on the transect, it records temperatures characteristic of the Gulf Stream. And we estimate that during this period, the model and glider estimates differ spatially by up to 12 to 16 miles. But between January 10th and 16th, you can see that the model records the glider as being pretty far inside of the Gulf Stream, but the transect records that the model significantly overestimated the temperature of the ocean at this place at this time. And during this period, we estimate that the model and glider estimates differ by up to 30 miles in some places, which is fairly significant considering the narrowness of the Gulf Stream. I do want to note that these estimates are very rough, and so the specific numbers should perhaps be taken less seriously than the implication, which is that RTOPS both underestimates and overestimates the extent of the Gulf Stream in a small geographic region, which hints at an underlying problem in how RTOPS trusts and assimilates glider data. So to summarize, overall, both NG657 and NG738 reported low quantitative errors, and both did reasonably well in areas that are decidedly outside of and decidedly inside of the Gulf Stream, and struggled mostly where the boundary between the Gulf Stream and kind of the normal ocean is undetermined. However, the model failed to properly resolve the landward edge of the Gulf Stream in at least one instance, sometimes by up to 30 miles, which indicates that the model is not sufficiently trusting of the observational data that these gliders are providing it and isn't assimilating it correctly. Areas of further research for us might include investigating whether the mean position of the Gulf Stream, and not just its landward edge, are not being properly resolved by these models because of errors in data assimilation. It might also involve comparing these results to those of other models, like the regionally constrained Doppio or GOFS, the Navy's ocean model, to determine whether this difficulty is in kind of a dynamics problem, or whether it's because of RTOP's specific data assimilation schema, which differs between ocean models. So thank you for everybody who contributed time, ideas, or materials for this project. Thank you all for being here, and a special thank you to my mentor and to my fellow REU students, as well as Stephanie Pert, Dr. Grace Massey, and Dr. Rochelle Seitz for organizing this program. If you have any questions, I would be glad to answer them. If I don't make it back in time for Q&A, you can contact me at the email address on this screen, and I would be more than happy to talk to you about my project. Thank you so much.